Good day and welcome to part one of our discussion on curve sketching. In this section, we will combine together the techniques and properties we've been discussing in the previous few sections to see if we can combine calculus and algebra to accurately sketch the graph of some given function. And what follows are a list of guidelines that will assist us in this endeavor. These guidelines do not need to be memorized. For a homework assignment, I might ask you to walk through the 8 steps, and in that case, you can look back at your notes or your book to see them. On the exam, I would explicitly spell them out. Say, Part A, find the domain. Part B, find the intercepts, and so on. So let's go ahead and kind of walk through the information that would be useful in terms of sketching the graph of a function. The first thing we might want to know is, what is a domain? So I'm simply just going to say, find that domain. And when we're finding the domain of a function, it's the typical things that we think about. Where is it defined? We cannot divide by 0. We cannot take square roots of negative numbers. If you have trig functions you're dealing with, there's certain built-in domains. Then we find the intercepts, both the y and the x. Recall the y-intercepts, in a sense, are maybe the easier ones to find because there's a single one, and it corresponds to the point 0, comma f of 0. That is, you simply need to determine when x is equal to 0, what is that corresponding point on your graph where it crosses the y-axis. And then similarly, to find the x-intercepts, you want to set y equal to 0. There can be many x-intercepts, and you find them by setting the equation f of x equal to 0 and simply solving for x. Once you have the domain and the intercepts, which you'll probably be adding on to an xy axis as you're working, the next thing to think about graphically would be symmetry. And there's two key types of symmetries that will assist us when it comes to sketching a graph. Is the graph of your function even, or is the graph of your function odd? So recall even, we're thinking whenever f of minus x is equal to f of x. And if this is the case, it tells us that the graph is symmetric about the y-axis. So an even function is symmetric about the y-axis. And there's a nice simple picture we can keep in mind. When we're thinking of an even function, we should maybe recall the graph of f of x equals x squared. The graph of x squared is nice and symmetric about that y-axis. That is to say, if you only had this right half, or simultaneously the left half of the graph, that's enough. You would reflect it about the y-axis, and you would have the entire picture. Similarly, we say a function is odd when f of minus x is equal to minus f of x. So we think an even function is going to absorb that minus sign. An odd function kind of spits out that minus sign. And an odd function has a graph which is symmetric about the origin. So an odd function is graphically symmetric about the origin. And once again, there's a basic graph we can keep in mind. We can simply think of the graph of x cubed. And if we're thinking of the graph of x cubed, note it looks roughly something like this. And what does it mean to say that the graph of this is symmetric about the origin? That is to say, if we start off with just half of the graph, what's going on with x cubed in the first quadrant, we would take that and we would first reflect it about the y-axis. And then once you have that reflected about the y-axis, you reflect it again about the x-axis, and that is what it means to be symmetric about the origin. But in either case, the big takeaway, if you have half the graph, by using reflections, you can get the other half. So in a sense, it cuts down the work which is required. Once we have the domain, the intercepts, we know the symmetry, now we can get to some things that are more familiar with our recent discussions. We can find the asymptotes. So remember, we have a horizontal asymptote, which is a line, y equals L, if the limit as x approaches plus or minus infinity of the function is equal to L. So in this step, we have to go back to our previous section and actually calculate two of these limits to determine what is the behavior of the function way to the right or way to the left. Vertical asymptotes, on the other hand, are going to be lines of the form x equals a. And x equals a is a vertical asymptote if one of a few possible limits are satisfied. The limit as x approaches a from the left of the function is equal to plus or minus infinity, or the limit as x approaches a from the left of the function is equal to plus or minus infinity. And we haven't gone into much detail yet with vertical asymptotes, but these are somewhat familiar and they occur in a very typical fashion. So I'll say that vertical asymptotes typically occur at a value x equals a when f of x, the function of interest, is undefined at a because you are dividing by 0. And if you want to think of the simplest possible example that we could come up with, note x equals 0 is a vertical asymptote of the function 1 over x. 1 over x is undefined at 0 because you're dividing by 0. X equals 0 is a vertical asymptote. And we will encounter these more in a few upcoming examples. And now it's to the pure calculus properties that we've been discussing. We find the intervals of increase-decrease, which note requires us to determine the first derivative. Where is it positive, where is it negative? But when you're determining where that first derivative is positive or negative, and maybe making a number line to assist you, you will first determine where that derivative is equal to 0. So simultaneously, you should also be able to classify critical points as local maxes and mins, but more specifically, you will also want to determine what are the points that are going to lie in your graph. Because when you have x-intercepts, y-intercepts, locations of maxes and mins, all of a sudden we can give a fairly accurate sketch of our graph. Then you find intervals of concavity by determining the second derivative, setting it equal to 0 to help find inflection points, intervals of concave up, intervals of concave down. And once you have all of this information, you should be able to sketch an accurate representation of the curve. Now, there are two distinct parts to these problems. There's part one, which is really the information gathering portion of the problem, gathering all of this information that we're discussing, steps 1 through 7. Then there's the secondary problem of taking all that information, compiling it together, and sketching a graph. So let's go ahead and look at one of these secondary types of problems where we can give you some information and ask you to sketch a related graph. In this section, we encounter, very broadly speaking, I'll say two big types of problems. One where we give you a nice specific function and ask you to use the curve sketching guidelines to sketch the graph. Or we may also just give you some information and say, based upon this information, can we sketch the graph? So we are told the following information, and let's see if we can just go through this step by step to get an idea of what our graph will look like. So we're told that f prime of 2 is equal to f of 0, which is equal to 0. So the fact that we have f of 0 equals 0 indicates a single point on our curve that we can start with. And because we know f prime of 2 equals 0, that's indicating that x equals 2 corresponds to a critical point. Then we are given some information about the first derivative, second derivative, a horizontal asymptote, and the fact that the function is odd. And because it's an odd function, we can simply sketch what happens to the right of 0 and then do a couple reflections to get that left half of the graph. So let's think about what the first derivative tells us. It's positive on the interval from 0 to 2, and what that indicates is that our function will be increasing on 0 to 2, and it is negative, i.e. a decreasing function, on the interval from 2 to infinity. And I'm going to try to encode this information below our axes. So from 0 to 2, we are increasing, and after 2, we are decreasing. And note that corresponds really nicely with the fact that we have some type of critical point at 2, and if you combine that together and you think you increase up to 2 and you decrease after, we could even take our observation further and say x equals 2 is a critical point. It's a local max by the first derivative test. Similarly, in terms of intervals of concavity, the second derivative is positive on 4 to infinity, which means it's concave up on that interval, and it's negative on 0 to 4, meaning it's concave down on that interval. So in terms of concavity, our graph is going to be concave up from 4 to infinity and concave down from 0 to 4. So we should now be able to put all of this information together. Starting at this point 0, 0, what will the curve look like? We are increasing in concave down until we hit that local maximum that occurs at 2. Then we begin decreasing while still remaining concave down, but when we get to x equals 4, we switch to concave up and we remain decreasing and we approach that horizontal asymptote, y equals 0. So to help myself sketch and get this concavity, I will usually put a very light dashed line representing where that concavity changes. So I start off at 0, 0, I'm increasing concave down until I get to that local max. And note, we can't sketch this graph with 100% accuracy because I have no idea what that local maximum value is. So up to some type of vertical scaling, this is what we should expect to see. Then we begin decreasing, and we remain concave down until right at this dashed line, we switch to concave up, and we approach that horizontal asymptote of y equals 0. And as usual, we're not shooting for perfection, but we just want to get that key information in the graph. And the last part here is to take into account the fact that we have an odd function. So if I want to graph what happens to the left of 0, we need to do a couple reflections to get into account this origin symmetry. So we need to first reflect this graph about the y-axis. So roughly speaking, it looks like we should be up here, switch concavity, and remember, perfection's not the goal, but to really kind of get that key ingredients. And if we were told we had an even function, this is exactly what the graph would look like. Because it's odd, we need to reflect it one more time now about the x-axis. So roughly speaking, something along those lines. Hopefully this gives you an idea of how we can take some amount of information and use that to give a rough but accurate sketch of what the graph of a function satisfying that information would look like. And this is most definitely a type of question we can encounter on future homework assignments or even exams. In our next video, we will investigate a single example where we are given a function and we go through all 8 of our guidelines on curve sketching to get an accurate sketch of the graph. So stay tuned and take care.